You hear about alien visitations in movies, Hollywood spaceships with blazing engines and chrome hulls, but what if they're already here, hidden in plain sight? What if they don't look like ships at all? What if they look like rocks? July 1st, 2025. The Atlas telescope in Chile spots something moving fast, really fast, 245,000 kilometers per hour, fast. That's the fastest object ever detected in our solar system, faster than any comet we've ever seen, faster than any asteroid. Too fast for gravity alone? The orbital calculations come back impossible. This thing didn't come from the asteroid belt. It didn't come from the Kuiper belt. It came from interstellar space, deep space, the void between the stars. Only the third object like this we've ever found. They call it 3I Atlas. If you value documented space, science, and astronomy like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's official 3I Atlas mission reports published September 2025, and the peer-reviewed James Webb Space Telescope spectroscopy data published in the European Research Repository Zenodo on August 25th, 2025. With additional confirmation from the Hubble Space Telescope imaging campaign documented by UCLA astronomer David Jewett. Now back to the information. Here's what makes 3I Atlas different. It's moving at 58 kilometers per second relative to the Sun. That's hyperbolic escape velocity. It entered our solar system around 8,000 years ago, roughly when human civilization started documenting history on Earth. Its orbital plane lies within 5 degrees of Earth's orbital plane. The odds of that happening randomly. 0.2%. Think about it. All of three-dimensional space. All the possible angles an interstellar object could approach from, and this one just happens to align almost perfectly with Earth's orbit. Harvard astrophysicist Avi Loeb noticed something else. 3. Atlas passes remarkably close to Venus, Mars, and Jupiter during its journey. The probability of all those close encounters happening by chance? Less than 0.005%, 1 in 20,000. Those aren't accident numbers, those are reconnaissance numbers. The James Webb Space Telescope trained its instruments on 3I Atlas in August 2025. What it found was wrong. The spectrum showed a carbon dioxide-dominated coma with a mixing ratio of 7.6 to 1 compared to water. That's among the highest ever measured in any comet. Most comets are water-rich. This one barely has water at all, just carbon dioxide gas streaming off its surface like industrial exhaust. The Spherex Space Telescope mapped the carbon dioxide plume extending 348,000 kilometers from the object, nearly twice the distance from Earth to the Moon. But here's the problem. No carbon monoxide detected, no water ice signatures, just pure carbon dioxide. That's not how natural comets work. Natural comets sublimate multiple compounds as they warm up. This one releases a single industrial gas. Hubble Space Telescope imaged 3I Atlas on July 21st, 2025, from 277 million miles away. The pictures show a teardrop-shaped cocoon of material coming off the object, but no tail. Comets have tails. That's what comets do. Solar radiation pressure pushes dust particles away from the nucleus, creating the characteristic tail pointing away from the Sun. 3. Atlas has no tail. The dust particles seem to evaporate too quickly to form one, as if they're not real dust at all. The nucleus size estimates keep changing. Early calculations suggested 20 kilometers in diameter, way too big for an interstellar asteroid. We should have detected 1 million smaller objects before finding one this large. But Hubble's high-resolution images constrain the nucleus to between 440 meters and 5.6 kilometers. Still massive, still rare, still moving impossibly fast. The Very Large Telescope in Chile detected something else in August 2025. Cyanide emission lines in the spectrum, hydrogen cyanide gas venting from the object, plus nickel vapor, atomic nickel. You don't get atomic nickel from ice sublimation. You get atomic nickel from industrial processes, from metal being heated to extreme temperatures. 3. Atlas started outgassing at 6.5 astronomical units from the Sun. That's beyond Jupiter's orbit. Most comets don't activate until they're inside 5 astronomical units. This one turned on early. Too early. As if something inside was powering up systems. The Transiting Exoplanet Survey satellite found pre-discovery images of 3I Atlas, dating back to May 2025, 2 months before official discovery. The object was already active, already outgassing, already moving through the dense star fields of Sagittarius constellation. Easy to hide among the background stars, perfect camouflage. Mars Reconnaissance Orbiter will get the best view. October 3rd, 2025. 3. iAtlas passes 29 million kilometers from Mars. The high-rise camera will image it with 30-kilometer resolution per pixel, 2 orders of magnitude better than Hubble. If there's anything artificial about this object, Mars will see it. The trajectory analysis reveals something else. 3. iAtlas approaches the Sun during solar conjunction. That means it passes behind the Sun from Earth's perspective during perihelion, October 29th, 2025. The perfect time to perform what aerospace engineers call a reverse Oberth maneuver. Fire engines, while hidden behind the Sun, change trajectory, become a permanent resident of the solar system instead of passing through. No one's claiming it will happen, but the geometry is perfect for it. The chemical composition tells a story. Carbon dioxide rich, water poor. Cyanide emissions, nickel vapor, industrial gas signatures. This isn't the ice and rock mixture we expect from natural comets. This is something else, something processed, something manufactured. NASA's official position remains clear. Tom Statler, lead scientist for Solar System Small Bodies, states it looks like a comet, does comet things, and very strongly resembles comets we know. But he admits it behaves differently from solar system comets. Different chemistry, different activation distance, different dust emission patterns. The scientific community splits 2 ways. Most astronomers point to the coma and outgassing as proof of natural cometary activity. The spectroscopic data confirms volatile compounds sublimating as the object approaches the Sun. Classic comet behavior. Case closed, but the dissenting voices grow louder. The unusual chemical composition, the perfect orbital alignment with Earth, the close approaches to multiple planets, the early activation, the lack of proper tail, the industrial gas emissions. Add them up, and they paint a picture that doesn't look entirely natural. The dark forest hypothesis offers one explanation. Advanced civilizations remain silent to avoid detection by potential threats. They explore using camouflaged probes that look like natural objects. Asteroid hulls provide excellent radiation shielding. They appear externally to be rocks while hiding advanced technology inside. If Earth is a target, trajectory corrections could occur behind celestial bodies, remaining hidden from view, only becoming detectable once the object emerges again. The geometry of 3 iAtlas allows exactly this kind of hidden maneuvering during its passage behind the Sun. 3 iAtlas will reach perihelion on October 29th, 2025 at 11:44 Universal Time. 1.36 astronomical units from the Sun, just inside Mars orbit, moving at 68 kilometers per second. Maximum speed, maximum stress on any internal systems. After perihelion, the object emerges on the other side of the Sun, visible again in December 2025. Still outgassing, still moving at escape velocity, still heading out of the solar system toward the constellation crater, unless it changes course during solar conjunction. The Mars flyby happens October 3rd. Europa Clipper and JUICE spacecraft will observe the object in November. Multiple space telescopes continue monitoring. The data stream doesn't stop. Every measurement adds to our understanding of what 3 iAtlas really is. The pre-discovery observations reveal something crucial. Zwicky Transient Facility captured images of 3 dies. iAtlas back to May 21st, 2025. Over 2 months before official discovery, the object was already there, already moving, already glowing. Hidden in the dense star fields of Sagittarius, where it would be nearly impossible to distinguish from background stars. Computer models trace its trajectory backward through the galaxy. The results are staggering. 3. iAtlas may have originated from a region of space formed 9 to 13 billion years ago, during what astronomers call cosmic noon, the peak era of star formation in our galaxy. This object could predate our solar system by billions of years. The age implications multiply the mystery. If 3 iAtlas formed 13 billion years ago, it has been wandering interstellar space since before Earth existed, before the Sun condensed from a molecular cloud, before any planets formed in our stellar neighborhood. A cosmic wanderer from the dawn of galactic time. The size mystery remains unsolved. Is the nucleus 500 meters across? 5 kilometers? 20 kilometers? The answer determines everything else. A 500-meter nucleus means most of the brightness comes from coma material. A 20-kilometer nucleus means we're looking at something the size of a small city moving through interstellar space. Early brightness calculations suggested 20 kilometers diameter for a typical asteroid albedo of 5%, but that creates problems. Interstellar space should contain millions of objects the size of One-Eye Oumuamua for every 20-kilometer object. The size distribution doesn't work. It's statistically impossible. The Hubble observations change the numbers. High-resolution imaging constrains the nucleus between 440 meters and 5.6 kilometers. Still large, still rare, but mathematically possible. The brightness measurements suggest 99% comes from the coma material, not the nucleus itself. But even the smaller size estimates create anomalies. A 5-kilometer nucleus carries 1,000 times more mass than Borisov, the previous interstellar comet. The surface area ranges from 100 times larger for a 5-kilometer diameter to 10,000 times larger for the maximum size estimate. Yet the activity level remains remarkably weak when calibrated per unit surface area. The dust production rate measurements show 30 kilograms per second of material streaming off the object as of July 2025, consistent with comet activity, but the material composition remains wrong. Too much carbon dioxide, too little water, too many industrial compounds. The Very Large Telescope spectroscopy from August 21st, 2025, confirmed hydrogen cyanide emissions, industrial poison gas venting from the object, plus atomic nickel vapor at temperatures exceeding 1500 degrees Celsius. Natural ice sublimation doesn't produce atomic nickel. Metal smelting does. The carbon monoxide absence puzzles scientists. Most carbon-rich comets show strong carbon monoxide signatures. 3. I-Atlas shows none. 0 carbon monoxide detection despite abundant carbon dioxide. That's backwards from natural comet chemistry. It suggests the carbon dioxide comes from a different source than ice sublimation. The water-ice detection remains marginal. James Webb Space. Telescope found traces of water vapor and water ice, but at levels far below normal comets. The water to carbon dioxide ratio sits at 1 to 7.6. Natural comets typically show the reverse. Water dominates. Carbon dioxide appears as a minor component. This object flips the chemistry. The outgassing pattern shows directional bias. Enhanced carbon dioxide emission points sunward, not uniformly distributed around the nucleus. Targeted venting, controlled emission, natural sublimation creates spherical outgassing patterns. This shows structured geometry. The transiting exoplanet survey satellite data reveals early activation. Tests detected 3 I-Atlas, outgassing at 9 astronomical units from the Sun. Most comets remain dormant beyond 5 astronomical units. This one turned on early. Too early for natural ice sublimation driven by solar heating alone. The brightening curve shows anomalous behavior. 3 I-Atlas follows a negative 3.8 power law for brightness versus distance, steeper than normal comets, more consistent with dynamically processed objects, comets that have made multiple passages close to stars. But this is supposedly a pristine interstellar object making its first solar encounter. Ground-based telescopes lost 3 I-Atlas in late September as it approached solar conjunction. The object disappeared behind the sun's glare exactly as orbital mechanics predicted. Nothing suspicious about that, but it creates a perfect window. 6 weeks of invisibility. 6 weeks when anything could happen. The conjunction timing enables clandestine maneuvers. Spacecraft engineers call it the reverse Oberth effect. Fire engines, while hidden behind the sun, to change trajectory undetected. The geometry of 3. I-Atlas allows exactly this kind of hidden course correction during perihelion passage. December 2025 will tell the final story. When 3 I-Atlas emerges from behind the sun, its trajectory will reveal everything. Still on the same hyperbolic orbit heading for interstellar space, natural object confirmed. Altered trajectory showing it captured into a solar orbit. Questions multiply. The Mars Reconnaissance Orbiter observations become critical. October 3rd, 2025, 3 I-Atlas passes 29 million kilometers from Mars. The high-rise camera resolution reaches 30 kilometers per pixel, 200 times better than Hubble Space Telescope imaging. If anything artificial exists within the coma, Mars will detect it. The timing coincidence disturbs some researchers. 3. I-Atlas entered the outer solar system approximately 8,000 years ago, roughly corresponding to the development of written language and complex human civilization on Earth. Advanced agriculture, permanent settlements, the foundation of recorded history. Statistical analysis shows the probability of such timing occurring randomly approaches 0. An interstellar object arriving precisely when Earth civilization reaches technological adolescence defies coincidence. Either the universe has remarkable timing, or something else explains the correlation. The orbital mechanics reveal additional anomalies. 3 I-Atlas approaches within 0.65 astronomical units of Venus, 0.36 astronomical units of Jupiter, 1.8 astronomical units of Earth. Multiple close planetary encounters during a single passage through the inner solar system. The probability of such a trajectory occurring naturally measures less than a 0.005%. Planetary reconnaissance requires exactly these kinds of orbital geometries. close approaches to multiple worlds, optimal observation angles, maximum data collection opportunities. The trajectory of 3. iAtlas provides textbook reconnaissance geometry for surveying Earth, Venus, Mars, and Jupiter during a single mission profile. The nuclear option exists. Planetary defense protocols exist for exactly this scenario. If 3 iAtlas shows signs of artificial maneuvering or hostile intent, multiple space agencies have contingency plans, nuclear interceptor missions, kinetic impactors, deflection strategies. The infrastructure exists to respond to threats from space. But those plans assume we recognize the threat. They assume hostile objects look hostile. They assume alien technology looks alien. What if it looks like a rock? What if it looks like ice and gas venting naturally from a comet nucleus? What if perfect camouflage means we never know for certain? The camouflage hypothesis gains credibility from military analysis. Defense researchers note that asteroid holes provide excellent natural shielding against cosmic radiation and micrometeorite impacts. Hollow out a small asteroid. Install life support systems and propulsion Rs, and you have the perfect interstellar reconnaissance vehicle. Undetectable, unsuspicious, hidden in plain sight. The stealth capabilities multiply when you consider detection methods. Ground-based telescopes identify objects by reflected sunlight. They look for motion against background stars. They measure brightness changes in orbital mechanics. A spacecraft disguised as an asteroid appears identical to a natural object, using all conventional detection methods. Active camouflage becomes possible with controlled outgassing. Release carbon dioxide at calculated rates to simulate natural comet activity. Create a false coma to mask the underlying structure. Emit industrial compounds at levels that mimic exotic ice compositions. Perfect the deception by matching expected comet behavior patterns. The technology requirements remain within theoretical limits. Ion propulsion systems could provide the observed acceleration signatures. Reactor cooling systems could explain the carbon dioxide emissions. Atmospheric processors could account for the industrial gas signatures. Nuclear thermal systems could generate the observed nickel vapor emissions. Current human technology approaches these capabilities. Ion drives power multiple spacecraft missions. Nuclear reactors operate in space environments. Closed-loop life support systems function on the International Space Station. Scale up the technology by a few centuries of development, and artificial interstellar objects become engineering problems rather than theoretical impossibilities. The detection challenge multiplies with advanced technology. If a civilization can build interstellar spacecraft, they can certainly master stealth techniques, radar absorption materials, thermal signature control, electromagnetic emission suppression, active countermeasures against optical detection. Perfect camouflage becomes achievable with sufficiently advanced engineering. 3. iAtlas represents the ultimate test case. Natural or artificial, comet or spacecraft, coincidence or reconnaissance, the data points both ways. The chemical signatures suggest industrial processes. The outgassing suggests natural sublimation. The trajectory suggests intentional targeting. The orbital mechanics suggest gravitational dynamics. The observational evidence creates a perfect stalemate. Every anomaly has natural explanations. Every natural explanation has problems. The carbon dioxide dominance could indicate exotic ice compositions or industrial cooling systems. The early activation could show unusual sublimation, physics, or artificial outgassing. The trajectory alignments could represent statistical flukes or intentional navigation. The scientific method demands extraordinary evidence for extraordinary claims. Fuzzy spectroscopy and suspicious trajectories don't qualify as proof of alien technology, but they don't disprove it either. They leave the question open. They keep the hypothesis alive. Multiple space agencies coordinate observational campaigns. NASA, ESA, JAXA, and private observatories pool resources and data. The scientific collaboration ensures no detail gets overlooked. No measurement goes unanalyzed. No anomaly remains unexplained. If 3 iAtlas hides secrets, combined human technology will find them. The timing pressure increases as perihelion approaches. October 29th, 2025, 11:44, universal time, maximum solar heating, maximum outgassing. Maximum stress on any internal systems. If 3 iAtlas contains technology, the thermal environment will test its limits. Infrared telescopes monitor temperature distributions across the object. Hotspots could indicate internal heat sources, cooling systems, power generation. Active thermal management. Natural comets show predictable heating patterns. Artificial objects show thermal signatures of their internal systems. Radio telescopes scan for electromagnetic emissions, transmissions, navigation signals, computer systems, communication attempts. Natural objects remain radio silent except for thermal noise. Artificial objects leak electromagnetic signatures despite shielding attempts. The radio spectrum holds clues invisible to optical telescopes. Gravitational measurements track trajectory changes. Natural objects follow predictable orbital mechanics. Artificial objects show course corrections. Station-keeping maneuvers, attitude adjustments, tiny accelerations that compound over time into major trajectory modifications. The gravitational signature reveals propulsion systems. Spectroscopic analysis continues throughout the approach phase. New compounds appear as internal temperatures rise, industrial chemicals, exotic materials, technological signatures. Natural objects sublimate predictable ice compositions. Artificial objects vent whatever keeps them operational. December 2025 approaches. 3I Atlas will reappear in the morning sky before dawn. Telescopes will track its position, measure its velocity, confirm its trajectory. The moment of truth arrives when orbital mechanics either confirm natural behavior or reveal something else entirely. The post-perihelion observations become crucial. November 3rd, 2025. 3. I-Atlas emerges from solar conjunction visible in the pre-dawn sky near Venus and Spica. Telescopes immediately lock onto the target. First priority measurements focus on orbital elements. Has the trajectory changed? Do the orbital mechanics match pre-perihelion calculations? Any deviation from predicted orbits indicates propulsion. Natural objects follow gravitational physics with mathematical precision. Artificial objects show tiny accelerations from attitude control thrusters, station-keeping maneuvers, or course correction burns. Even microaccelerations compound over interplanetary distances. The brightness evolution provides additional clues. Natural comets follow predictable brightness curves as they move away from the sun, decreasing outgassing, dimming coma, predictable fade rates. Artificial objects might maintain brightness through active systems, internal power sources, continued emissions, thermal management requirements. European Space Agency spacecraft provide unique observation opportunities. Mars Express and ExoMars. Trace Gas Orbiter observed from Mars orbit during the October 3rd close approach. Jupiter Icy Moons Explorer conducts observations in November while en route to Jupiter. Europa Clipper coordinates ultraviolet spectroscopy campaigns. Multiple spacecraft observe simultaneously from different locations. The distributed observation network eliminates parallax errors and detection gaps. If 3I Atlas shows artificial behavior, multiple independent observers will confirm the measurements. Triangulation fixes precise positions. Doppler measurements track velocity changes. Spectroscopic analysis reveals compositional evolution. The December observations focus on tail development. Natural comets develop pronounced tails after perihelion as heating effects continue. Solar wind pressure shapes the tail geometry. Dust particle distributions create characteristic patterns. 3. I-Atlas should show a normal tail development if it contains natural ices and dust. Artificial objects might show different tail characteristics. Controlled outgassing creates different particle distributions. Industrial compounds produce different spectroscopic signatures. Thermal management systems create different temperature profiles. The tail morphology reveals the underlying physics. Ground-based observations coordinate with space missions. Professional observatories dedicate telescope time to 3. I-Atlas monitoring. Amateur astronomers contribute imaging data. Citizen science projects analyze spectroscopic measurements. The distributed observation network maximizes data collection opportunities. The data analysis pipeline processes measurements in real time. Automated systems flag anomalies. Machine learning algorithms identify pattern deviations. Human experts verify artificial intelligence findings. The analysis speed ensures rapid response to unexpected discoveries. International protocols govern discovery announcements. The International Astronomical Union coordinates official designations. NASA manages public communications. Scientific journals prepare peer review processes. Media outlets receive briefings on significant findings. The information flow balances scientific rigor with public interest. Until then, we watch, we measure, we calculate, we prepare for both possibilities. Natural comet heading home to interstellar space, or something else entirely. Hidden in plain sight, using perfect camouflage to mask its true nature while conducting reconnaissance on the third planet from the sun. The implications cascade through multiple disciplines. Astrobiology considers the possibility of first contact through reconnaissance probes. Planetary defense evaluates response protocols for artificial interstellar objects. International law addresses sovereignty questions for alien technology in Earth orbit. The philosophical questions multiply faster than scientific answers. If 3I Atlas represents alien technology, what does that mean for human civilization? Are we being studied, evaluated, prepared for contact? The questions outpace our ability to answer them with current evidence. The cosmos keeps its secrets well. 3. iAtlas might be just another ice ball from deep space. Or it might be our first confirmed contact with technology from another star system. We'll know for certain in December. Until then, every measurement matters. Every spectrum reveals clues. Every orbital calculation brings us closer to the truth about what's really passing through our solar system disguised as a comet. The search for truth continues across multiple wavelengths and observation platforms. Radio telescopes listen for signals. Infrared detectors map thermal emissions. Optical telescopes track position changes. Spectroscopic analysis reveals chemical compositions. The multi-spectrum approach ensures comprehensive coverage. The answer lies waiting in the data, hidden in the numbers, buried in the spectral lines and orbital elements and chemical compositions. December will reveal whether we're witnessing a natural celestial mechanics or something far more profound. Something that changes everything we thought we knew about our place in the universe and whether we're truly alone among the stars. But the final revelation may come not from distant observations, but from close encounter data. The Mars Reconnaissance Orbiter images, the spacecraft observations during perihelion passage, the post-conjunction measurements of trajectory changes. The devil hides in the details that only high-resolution observations can reveal. If 3i Atlas carries secrets, they will emerge in the coming months through careful analysis of unprecedented data. Never before have so many advanced instruments observed an interstellar object with such precision and coordination. The truth cannot hide forever when subjected to such intense scientific scrutiny.